great pleasure to introduce Professor Henry Tai. If you didn't put down this 代字海, you would never have really told yourself what that TY is. But first of all, I think he has a brilliant father to pick up this name. Anyway, Henry Tai, Professor Tai, actually he's the director, another semi-joke at the beginning, when people are still sitting there. He's the director at Hong Kong University of Science and Technology, the so-called Jockey Club Institute for Advanced Study. I think they study jockeying. Anyway, so Professor Tai was born in Shanghai but brought up in Hong Kong. And he received his PhD in 1974 from MIT, and then spent postdoc terms at SLAC and at Fermilab before going to Cornell in '78. And he became full professor there, and I think a chair professor in 1987. I think he's really very versatile. He did QCD, Laconian early on, and then moved to strings and cosmology. Actually, he has a big influence on inflation. Maybe in the evening, for some people we can talk about it. And but I think he always kept a logical touch. And so I think probably related to the talk today, probably he's best known for his brain cosmology, how the world really began. So in 2007, he became an APS fellow, and in 2011, he came back to Hong Kong, picked up the current position. So he's the director. Actually, in Chinese, it would be a 跑马会高等研究院. 跑马会高等研究院院长. So it's a very powerful title, and if you look at the notice, he has a one-line abstract, so that's very stylish. Okay, Professor Tai, the floor is yours.
Is it on? Okay. It's my great pleasure to visit this university. When I was a student at the United States, all the Chinese students who are top-notch all come from this university. And I know many of them, and I was very impressed, and I'm so very happy to visit this university. This is my second time. So. Okay, so I'm going to talk about the origin of the universe, and I should state very clearly that this is a scientific talk, and not philosophical or religious talk. So let me just summarize for you what we understand today in terms of scientific observations. That our whole universe came from nothing. And that happened 13.8 billion years ago. And by nothing, I do not mean vacuum. Vacuum still have space. So by nothing, I really mean not even space. Okay, this is better. So, and I'm going to explain how we come to this conclusion. And I would say that this picture of this understanding is accepted by most cosmologists today, but not all. And when I want to explain absolutely nothing, that part I need to say a few words to clarify that. But otherwise, if you don't get anything out from this talk, at least you can remember this is the best we understand today of our universe. So, first of course, what do we mean by universe? And I think the Chinese definition is probably the best that I can think of. Okay, essentially means all of space and time. That's our universe, and of course everything in it. So we start from gravity, which we all know very well. Newton invented gravity theory, which has the apple dropping from a tree in Cambridge, in England, and then from that he deduced the gravitational force and used that to explain why everything will fall on the surface of the Earth and how planets will go around the sun. It's a very successful theory in the 17th centuries, 18th centuries, even 19th centuries. Now we go back to where we are today. So I first described where we are today. Before I go ahead to talk about the origin of the universe, because there's a couple of things I want to bring to attention and get prepared to move back in time. So there are about 400 billion stars in our galaxy. Our galaxy is called the Milky Way, and you look at the night sky, some nights you see hardly any stars. That's because you're looking in a direction that's pointing out. We are somewhere in the arm of our galaxy. This is not our galaxy because we're inside, we can take this picture. But this is a galaxy very similar to ours. And so if you look out, you see a sky with hardly any stars. And then some nights, you see the Milky Way, lots of stars. That's when you look towards the center of our galaxy. Okay? So this galaxy is very much like ours. And there are many billions of galaxies in our universe. So that gives you some idea about the vastness of our universe as far as we can observe today. So a convenient way that we're going to use is that instead of using numbers like this, our speed of light, we always like to write this way. And because sometimes to count how many digits is not so easy, and this way sort of make everything much more easily understood. So, and we will talk about the origin of the universe. So we'll go back to a time when the universe is of this order of magnitude in time. So this is really a tiny instant at the beginning of the universe. And we'll go back to that. But before, let me remind you that Einstein's special relativity theory tells us that mass and energy are equivalent in some sense. And we will use that every now and then, something that I assume everybody knows very well. So the theory of general relativity today, this year, is the 100th anniversary of Einstein's theory of general relativity. And before his proposal, we know that the planets move according to Newton's gravitational force law. And Einstein asked a very simple question. Since there's nothing in between the Earth and the Sun except empty space, how does the Earth know about the gravitational pull of the Sun? A very simple, innocuous question. But when you think deeper about it, and Einstein did, he realized that there's space. So space somehow had to do something, and that's essentially the theory of general relativity. I think many of you have seen this picture to illustrate what's going on. That is, you put a bowling ball on a mattress, for example, which used to be flat, but a bowling ball will dim it, so change the surface of the mattress so that instead of flat, become curved. And if you now bring a marble in, the marble will not go straight, but will try to move such that as if it's falling towards the bowling ball. If you remove the mattress or try to hide it, then you will think that there's a force between the marble and the bowling ball, but in fact, Einstein will interpret differently that the bowling ball is warping space. Of course, Einstein referred to three-dimensional space and actually time. And then the marble will feel that warp, and so you move in a way as if it's moving towards each other, as if there's attractive force. This provides an alternative description that Newton's gravity theory have functioned so well for many years. And by now, we essentially accepted Einstein theory for a variety of checks observationally. So we accept the fact that space-time is an active player in terms of motions of particles and objects. In fact, space-time can be warped, curved, expand, shrink, and in some cases, you can describe something like this, like the presence of a black hole. And of course, Einstein's theory of general relativity played an important role in GPS as well. That's another topic. Now, after Einstein's theory of general relativity was more or less accepted by people around that time, partly due to the bending of light, Mercury perihelion, for example, Edwin Hubble looked at the galaxies and find that the further away a galaxy is, the faster it moves away from us. And the only way that you can explain this is that the universe is expanding. Again, here's a two-dimensional picture, illustrate this. Suppose these coins are the galaxies, and this two-dimensional represent the three-dimensional universe. As they expand, you find the space between the coins are increasing, and in fact, the further away one seems to move faster away from us, and compared with the closer one. And when that happened in all directions, as Hubble and later observations checked, the only reasonable explanation is that the universe is expanding. So, we have an expanding universe, and the question now is what's in our universe today? We can look out the sky and we can see all sorts of objects. We have atoms, molecules, electrons, photons, and essentially what we can see are made of these objects. And yet, it seems that the content of the universe contains not only ordinary matter. Ordinary matter is atom, molecule, electrons, photons, neutrinos, things that we know, Higgs bosons, gate bosons. It has other stuff. The ordinary matter contributes only 4 to 5% of the total content of our universe. There's two other components, which we call dark matter, which compose about 23, 25%, and then dark energy, which is 70% around. Okay? So we are familiar with only 5% of the content of our universe. The remaining 95% are totally obscure to us, even though we know they're present. And we call it dark matter and dark energy. Of course, if it's dark, how do we know that there are two different kinds of things? Why do we say there's a dark matter and dark energy? And the reason is because they behave differently. So let me think about a patch of sky, a patch of outer space. Either you can think about 3 galaxies or 3 atoms, doesn't matter, some matter. And the blueness is the energy density of the dark energy. The matter essentially have some of them. And suppose this expands to a bigger volume. This is 2-dimensional picture of a 3-dimensional volume I want to describe. The matter will move apart from each other. And so what happens to the matter density? as the volume grows, the matter density goes down because the amount of matter is conserved. The blueness stands for the dark energy. It turns out that as the volume grows, the dark energy density stays more or less constant. Okay? So that's how we know as the universe expands, look at how it expands, you can tell that there's a certain amount of dark matter and there's a certain amount of dark energy. Together they compose 95% of the content of our universe. So the dark energy is very strange here because as the volume increases by many folds, the dark energy density still stays more or less constant. Okay? And so it's a strange type of energy, but it's something that Einstein's theory of general relativity tells us we can easily introduce. And in fact, Einstein introduced once, he called it the cosmological constant, and later on he abandoned it. But now it seems that it's coming back in full force.
So we actually don't know its energy. We just call it dark energy.
It's energy, yes.
How do you know it's energy?
Because matter and energy curve the space. And so the expansion of the universe depends on how much energy content in it and what type of energy content. And we can follow the expansion of the universe over the ages so we know how it changed over a function of time. And so from that we deduce there's something called dark energy where its density does not change and the universe expands.
So dark energy, we cannot measure the density.
You measure by looking at the expansion of the universe.
That's right. But
So if it's not
a single universe,
if it's not cosmological constant, then it's something even stranger and not contained in Einstein theory.
my complaint is we don't know it's really energy. We call it dark energy, it's a bad name. It's cosmology constant, that's fine. Okay, that may be associated with the space-time.
Cosmological constant is nothing but an energy density that stays constant as the universe expands. So that's, you can say that's the definition nowadays we use.
If you choose that one. I still disagree.
Sure. We can go back to this. We can come back to this point later. Okay. What people measure is that the universe is expanding and people thought it's slowing down. And instead, people discover that the universe actually is expanding faster, which is called the accelerated universe. And the prevalent explanation of that is due to the presence of this dark energy density. Now there's other explanations over time, and more or less in the last 10 years, the other explanations, one by one, essentially have been ruled out. So, but it's not 100% certainty at this stage. Okay, so how is it possible that the volume grows while the energy density stays constant? Okay, that's possible because general relativity tells us that the dark energy or cosmological constant actually has a negative pressure. And it also tells us that expansion will become exponential. So not only expansion is growing, but you're growing from power-like to exponential. As the universe expands, so this is where the picture, we believe. In the early days, today is about here. The yellow part is ordinary matter, the red is the dark matter, and the blue is the dark energy. So this is the content of today. If you go back in time, you find that the dark matter and ordinary matter dominates. The blue, which is dark energy density, is only a small slice. But as we say, as the universe expands, the matter density goes down, but the dark energy density stays constant. That's why as the universe expands, the dark energy density dominates, and that's essentially why today there's like 70% dark energy density. And as we go further, the universe accelerating, the expansion accelerating, and then the universe will be totally dominated by the dark energy in the future, unless something unusual happens. Okay? And we don't know if that's going to be the case or not, but following, extrapolating at what happened for the universe in the past billions of years, and this is the consequence that eventually we'll end up with. That is, at a certain point, the dark energy will become 90%, 99% of the content of the universe. So this is the picture as of now. This explains also the accelerating universe that observed by Perlmutter, Schmidt, and Rice in 1998. And as I said, the most likely and more or less accepted explanation of dark energy is the vacuum energy, i.e. the cosmological constant that Einstein introduced. Okay? And in fact, Einstein introduced it to stabilize the universe, and when you know the universe is expanding, he abandoned it, and according to Gamow, he said that's the biggest blunder he made in his career. And so it's quite amazing that it's coming back in full force to dominate the energy content of the universe today, and it will play a big role in the origin of the universe that I'm going to turn to. So we all know that the universe is expanding, and as the universe expands, it's cooling off. That means if we go back in time, the universe is smaller and hotter. And you can easily extrapolate that, and that's exactly how the Big Bang Theory tells us to extrapolate. And you can go to a very high temperature. And then in order to have the right kind of expansion, in order to have the right kind of nuclei synthesis and a variety of properties, you can actually calculate that today's universe has a temperature of about 3 degrees Kelvin. Now, the absolute temperature, of course, is minus 273 degrees centigrade, so 3 degrees Kelvin is minus 270 degrees centigrade, but it's not zero. Okay, it's still, we're living in the heat bath of roughly 3 degrees Kelvin. That's calculated by Gamow and Alpha Herman around 1950. So it's a very clear prediction that that's the Big Bang Theory predicts, and if it's correct. So let me go back a little quantum physics that I think all of you know, but just to remind you, that we know waves behave like particles and particles behave like waves. So light or microwave are nothing but collection of photons. And electrons can behave like a wave, so it fluctuates, say, over a barrier or around a proton to form a hydroatom. So essentially, fluctuation, quantum fluctuation, is automatically a consequence in any quantum system that we are familiar with. And since we live in a quantum world, some fluctuation is unavoidable. And one of the big properties of quantum physics, in fact, probably the first one, is by Planck. He talked about the blackbody radiation spectrum. That is, if you have, say, 5,000 degree Kelvin, then this is the blue curve. This is the wavelength of the electromagnetic waves. And this is the visible range, and wavelength large, that's called the microwave, and ultraviolet here. And for any given temperature, there's a very clear curve, and this is the radiation spectrum. And temperature lower, the curve will be smaller and a little bit more of the long wavelength. Okay. So this is very, very clear that if you do one single measurement and one single wavelength, you can determine the temperature once you accept the Planck's blackbody radiation spectrum. Well, that turned out to be measured Penzias and Wilson, when they want to study communication from ATT lab using microwave. Now they so-called, our cell phone use microwave, and clearly this is a precursor to the using of microwave for communication. And they point their antenna and they find noise all the time. And the noise they have is there no matter which direction they point their antenna to. And then they realize that this is nothing but the cosmic microwave background due to the 3-degree blackbody radiation that we are in today, whole universe. So their measurement is 7.35 centimeter, and they measure some value like here. However, by now, this is much better measured. This particular curve is measured by Kobe satellite in 1993. And the green curve is the blackbody spectrum for object of above with temperature which is 2.7260 degrees Kelvin. The crosses are the data coming from Kobe. And this is spectacular success, confirming with no doubt that we are living in a thermal bath of temperature roughly 2.72 degrees Kelvin. I've exaggerated the error bars. So this little curve have error bars. Actually, the actual data error bars are much smaller. But if I put down the actual error bars, they will just be a tiny point such that you can't see it. So these are error bars blow up by 400 times. So you can see this accuracy is really unprecedented. And there's no way you can measure a blackbody curve to anything close to this in a room like this. So the precision really convert cosmology from a speculative subject to a precision science. And Mayer et al. Did that. And they can obtain, by now we have better measurements, that the age of the universe is 13.798 billion years. So very, very precise measurements we can do. So this is the Big Bang, and we talk about nucleosynthesis about the first few minutes, and now we say where it come from, right? If the Big Bang is the biggest explosion ever that created our universe, but if you have explosion, you always want to know what causes the explosion. Why something explodes? Okay. And this is precisely the question we want to know, where this hot Big Bang came from. And this is leading us further back in time, and we're going to go to, instead of an order of second, we're going to go to a much, much earlier time scale. So, how did the hot Big Bang started? And the prevalent theory accepted by most, but certainly not all cosmologists, is the so-called inflationary universe. So what does universe happen? It starts from a single point of size, tiny, much smaller than a single electron, with total energy much less than that of single electron. A tiny little bit of space and with tiny little bit of energy. But that energy is the same as the dark energy I talked about before. Okay. But with a value much, much bigger than today's observed dark energy density, much higher density. So what happened? Well, the universe will expand exponentially with the energy density more or less stay constant. So this point, tiny point, grow exponentially by many orders of magnitude, and driven by a much larger dark energy density.